So 6033 in the news, brought to you by Howie Schroeb this morning. So this is an exciting portion in 033 because we're starting to talk about security, and I will introduce that to you more formally in just a second. But when we get to the security section of 033, I never have to go searching for 6033 in the news segments. They just seem to happen. So this one is one that is pretty timely to what you're going to be talking about this week. It might not make 100% sense today, but definitely relevant to this week. So a couple of years ago, 2018, 2017, 2018, there were two big vulnerabilities discovered. Meltdown, which you're going to read about for Thursday, and then Spectre. And there are some solutions to both of these vulnerabilities, but it seems now that a lot of the systems and processes that were put in place to defend against Spectre in particular, we have found further vulnerabilities about them. So there is not yet a paper about this, but it's apparently forthcoming. Howie, do you know any more details about how any of this works?
No, I don't.
Yeah, that's okay. And the reason it's okay is because I think that this actually illustrates a theme that you're going to see throughout the next couple of lectures, which is that when it comes to computer security, we are kind of always racing against adversaries, right? So we will try to secure our systems the best that we can. Then some sort of vulnerability will be discovered. We will try to fix that vulnerability. Another vulnerability will be discovered, etc. All right. And so what we're going to try to talk about starting today for the next 3 weeks is, well, what do we do with that, right? How do we sort of deal with that? All right. So this today is the first lecture about security. We're going to talk about authentication, which is the process by which we sort of identify that users coming into a system are who they say they are. But let me give you just a little bit of a quick overview to security before we dive into that technical topic specifically, right? So we've come from a place the past couple of weeks in 033 where we've talked about building reliable systems despite failures. And we didn't always, we didn't do like a super precise analysis on all of this, but we typically thought of those failures as being more or less random and more or less independent, right? Machines failed with some probability, but we never imagined that there was, say, like a person out there trying specifically to bring down our system until today. All right, so now we're going to start to consider how to build systems that can deal with malicious attacks. And we're going to try to uphold some goal despite actions by an adversary. And even though, we've been dealing with, we have these techniques for dealing with failures, right? That's what we spent the whole last 3 weeks on. It's going to be tough to use them to deal with adversaries for a number of reasons. One is just that, one failure due to some sort of attack is probably one too many, right? So there are a lot of different things that make computer security unique, right? So first of all, the adversaries that we're considering, they might be trying to do all sorts of different things. There's a pretty big just like landscape of attacks, right? Adversaries might be trying to steal personal information. They might be trying to perform a phishing attack on you. They might have access to a botnet. They might be trying to infect a system with a virus. Right? There's all sorts of things they might be trying to do. These days, the internet makes these attacks fast, cheap, and scalable. So we're going to be eventually trying to combat adversaries that have a great deal of resources, right? Maybe they have access to a whole suite of compromised machines that are part of a botnet, right? So that could be like tens of thousands of machines, for instance. This also lets adversaries automate a lot of their attacks, right? So you will see cases where a system is compromised faster than users could react to it, right? The type of these adversaries is huge. Our adversaries are often anonymous, right? There's like a lot working against us in this part of the class. But one thing that is pretty important is that often users have poor intuition about computer security, right? They might misunderstand the implications of certain important security decisions, right? So the final thing that can make security really hard is that almost always it's a negative goal. So we're trying to achieve something despite what an adversary might do. So here, let me give you an example. So imagine that I have all of the grades for this class stored in like a grades.txt file, right? Here's an example of a positive goal related to that file. The positive goal might be that my goal is Karen can read grades.txt, right? And this is relatively easy to check, right? I will say, hey, Karen, can you log into this machine and tell me if you can read this file? Right? She will presumably say yes. Even if for some reason I don't trust her, we could watch her do that, and that's a pretty easy goal to have verified. But let me give you kind of a negative goal in that scenario. Right? Suppose my negative goal is, well, I want Karen to be able to read grades.txt, but I want Howie to not be able to read grades.txt. All right, so I could try to do the same thing. I could just ask Howie and say, hey, Howie, can you read this file? Right? What do you all think Howie is going to say? Assuming that he knows my goal is for him to not be able to read the file. It's like a secret to Howie. He's probably just going to say no, right? He'll say, no, of course not, Katrina. I can't read this file. Right? Do we trust Howie? Right? Do we believe that when he says, no, I can't read grades.txt, are we satisfied that, oh, okay, things are good. There's no way he could ever read this file, right? I mean, look, Howie's sitting there just, sipping his coffee. He looks so suspicious. How could we trust him when he says, no, I can't read this file, right? And indeed, we would have to reason about all the possible ways. See, look, that is what someone who can read grades.txt would say, right? They would say, I'm a nice guy, trust me, right? We would have to think about like, okay, well, Howie could just change the permissions in the file. Even if I had them set correctly, maybe he's a system administrator, he can just change the permissions, right? Or if he and Karen share accounts on the same machine, which is very reasonable to imagine, they both work at the same place, right? Howie could try to reuse memory after Karen's text editor exits. How we could call the system administrator, pretend to be Karen, reset her password, right? There's really no point at which we could stop, right? In general, we cannot say that Howie would never get a copy of this file, right? It is very, very hard to do this. It is very hard to consider all possible cases with an adversary, right? To reason about security in the face of a system with many complex goals, right? We're not going to leave this portion of 033 having like 100% perfectly secure systems, right? This is not something that we can get to, right? Instead, what we're going to do is we're going to try to teach you how to sort of think about systems in the context of security, how to assess various risks, how to make progress against very common attacks, all right? So that you, in some ways, make things harder and harder and harder for an adversary to do. Right, you're going to see a lot of trade-offs. You'll often see, say, security versus performance, security versus simplicity, or security versus convenience, right? Security does tend to add complexity to our systems, right? So how are we going to do this? How are we going to start by building these more secure systems? We're going to start by being clear about two things. And the first thing that we want to be clear about is our goals, right? Which in the context of security, we refer to as our policy. Right? Security policies differ depending on the system. We're going to do a long example of one today. But just to give you a taste, some common policies that you might want. You might want privacy, right? That means that you want to limit who can read data. You might want integrity, which is a limitation on who can write data. You might want availability, right? Which we've talked about. Ensure that a service keeps operating even in the face of certain attacks, right? And speaking of those attacks, along with whatever goals or policy we have, we want to be clear about the assumptions that we're making about our adversary, right? This is what's known as a threat model. So what are we protecting against, right? We don't always know in advance who might attack our systems or what they might do, right? And adversaries have different goals, techniques, resources, expertise, right? And we've seen an example with Karen and Howie. We're not going to be able to be secure against an arbitrary adversary, right? So we're going to need to make some plausible assumptions in order to make any progress here, right? Those assumptions are known as our threat model, right? So we might, for instance, make assumptions that an adversary controls maybe some computers or some networks in our system, but not all of them. We might make an assumption that an adversary controls some software on computers, but not the whole machine. We might just make the assumption the adversary knows some information, but sort of not all of the relevant information, right? And getting this threat model sort of correct, it's not easy, right? If we underestimate our threats, our system isn't going to be secure at all. But again, if we overestimate them, we just might not be able to make any progress, right? Also, as we go through this, we'll see that not all threats are equally important or equally likely, right? So it's generally a bad idea to be too over ambitious with your threat model. It's harder to design modular security solutions that kind of encompass everything, right? We're much more likely to have a solution for an adversary who has, say, access to a network, but not a particular machine, right? And then maybe a solution for an adversary who has access to the machine. And once we have a threat model, we can kind of build it up, we can evolve it, we can combine some of these solutions, right? So we're kind of going to apply a similar design process to what we've been doing here. So the way lectures are going to work, there are 3 weeks of security lectures. Yes, I'm looking at a calendar. There are 3 weeks of security lectures. In each week, we're going to talk about the challenges and solutions kind of from each module of O33. So for instance, this week we're going to spend most of our time talking about like lower level attacks. We're dealing with a single machine. Next week, we'll move to thinking about the network. And then the final week, we'll move to thinking about bigger distributed systems. This is going to feel a little bit less systematic than the rest of O33. That is because partly historically, the systems community hasn't always had a security first mindset, right? But additionally, I told you before, we're not going to achieve perfect security, right? Last time, we could go on a quest where we were going to get single copy consistency and we got it at the end, right? We're not going to go on a quest for perfect security. It would be like the rest of our lives. Right? But we can make improvements in some places. So let's start with what we're going to do today, right? So be clear about our goals and our assumptions. Let me tell you the goal for today, right? It's small because there's a lot more coming on this slide, right? So our goal for today is to provide authentication for users. Authentication means that we want to be able to verify that the user is who they say they are, right? At the same time, an attacker should not be able to impersonate the user. Right, we're going to focus on one of the, for most of this lecture, on one of the most common ways to authenticate users, right? Usernames and passwords, right? We're going to focus on this one. It's super common, all right? And we're even going to say some things about why that is at the end, right? And also a lot can go wrong, right? So this lecture is going to illuminate some common mistakes, right? But you all have usernames and passwords, all right? Some good things about usernames and passwords, they're relatively easy to use, like from a user standpoint. They're already deployed in lots of places, all right? So let's start with this idea, all right? So on this slide, as you can see, let me move my green box a little bit just so it's centered slightly better. There you go. All right, so you can see we have a bunch of different users here and a bunch of different passwords, all right? And before I even talk about our threat model, let's just, let's make sure that we understand just how a system would use this data to authenticate a user. All right, so suppose you show up to my system, right? This is my system. I've got this username password table stored. All right, this is how I would authenticate you. You're going to input a password. I'll look it up on my table and return whether they're equal. All right, you can see these passwords here, right? They're all, I generated these randomly. They're just random 16 character strings of all lowercase letters, right? It's quite unlikely that an adversary, right, who in this series of lectures, Howie is always going to be the adversary, because I think of all of the staff, he is the least likely adversary. And so it brings me a lot of joy to use him as an example. It's unlikely that Howie's just going to guess our passwords, right? So things are looking pretty good. But before we even define our threat model, I have a question for you all. Is this what passwords really look like? If I were to say, have access, and I don't have access, but if I were to have access to like the username and passwords for everyone at MIT, like your Kerberos password, do you think that there are all these nice randomly generated relatively long strings? Do you think that this is how users in the real world pick passwords? No, no, not so much. This is not what passwords really look like. And a lot of the reasons we have a good sense of what passwords really look like um, is because these systems get hacked all the time. So absolutely not. In reality, some passwords are far more common than others. And this is something that we are going to need to deal with today. So the way I have done this on the slide, a lot of the passwords are still random, but you can see that I've selected some common passwords, and we've got 7 of our users here using common passwords, right? I did all ones, 1, 2, 3, 4, 5, 6, the word password. Those are indeed very common passwords. There are a lot more, but we're gonna try to keep these users in mind as we go through. All right, so keeping that in mind, this is our kind of landscape of passwords. Now let me give you our threat model, because I actually want to do something a little bit stronger than just worrying about an adversary guessing our password. I want to think about an adversary that has access to the entire stored table. Right? There are lots of ways that an adversary might have access to this table. Maybe our adversary is actually a system administrator on this server, right? Or maybe they're not a system administrator, but they have access to the server and they've figured out other ways to read stored data. We will be talking about such ways on Wednesday and on Thursday. Right, so this is a pretty strong threat, but not an unreasonable threat. All right, so right away there's a problem. All right, right away there's a problem because the adversary with access to this table can just read the passwords. Right, my threat model right now is that I am storing these username and passwords in plain text on a server. The adversary has access to the server. This is terrible. This is not going to work at all. All right, do not store sensitive data on a server just in plain text. Like if you take nothing away from the security section of this class, there is the thing for you to take away. Just don't do that. That is a bad idea. All right, but now this gives us a little bit of a challenge. All right, the challenge is, okay, so we don't want to store these passwords in just plain text, but I've still got to be able to authenticate you, right? I run this server. Howie is our adversary. You all are users. I still want to know when you're logging in correctly, right? So how are we going to do that, right? We're going to do that by taking a brief interlude into the world of hash functions, right? So first of all, I have a quick poll. It is anonymous. I just want to see sort of where we're at in the world of hash functions, right? Have you heard of them, and do you know what they do? I have a special appreciation for the people who are picking maybe. I like that. Okay, I'll let this run for 4 more seconds. Okay, so this is cool. The vast majority of you have heard of hash functions, which is very cool. Many of you, but not all of you, know what a hash function does. That is totally fine, because by the end of today, you will know what a hash function does, at least for our purposes. In some ways, this lecture is like a bait and switch. You think it's on authentication. It's really about hash functions. Okay, so what do we need to know about hash functions? This is not a math class. We are not going to have time to go into all of the very cool mathematical and like cryptographical backing of hash functions. Right, but we're going to talk about the things you need to know to apply these. All right, I'm going to give you a spoiler because I don't want anyone to get worried. The first time we try this, it's not going to work. All right, it's going to take us 3 tries. So what do we need to know about hash functions? Hash functions take strings of arbitrary size, map them to fixed length strings. 256 bits, 512 bits, strings of a fixed length. Right, they do a lot of cool things. Here are some of the cool things. They are deterministic, right? If you take a string and you hash it, take the same string using the same hash function, you do it again, you're going to get the same result, right? There's no randomness that is an input into this process. If you hash the string Katrina over and over and over again with the same hash function, you're going to get the same result every time, right? They are collision resistant, which means that if you take two different strings and hash them, you are almost certainly going to get two different results. All right, so if you hash the string Katrina and the string Karen, you're going to get two different outputs. All right. The last, there's so many facts about hash functions. I could do 2 solid weeks on hash functions, but sort of one of the last things we need, they're one way. So if I give you a string, it's very easy to take the hash of the string. But if I give you only the output and I say like, hey, here's this output, tell me what string I hashed to get it. You can't, right? It is intractable to do that. Right. So this is, if you think about these in contrast to the types of functions that you might be familiar with, right? Hash functions are weird, right? This is not a function like f of x equals x squared, right? These are sort of weird, specially designed functions. And as a result, there aren't many of them, right? There are not that many hash functions out there. The ones that exist are well known. So what this means for us, if at any point we're going to try to apply hash functions, which we are in like 2 minutes, we can't rely on like having a secret hash function, like a hash function that our adversary doesn't know. There's no such thing, right? They're public. We all know them, right? You can, if you're really into these, you can look some of them up. They work sort of weirdly. I think they're very cool. They're going to be very useful for us. They're useful in lots of places in computer science. I'll bring up some others in a second, but we're going to try to apply this. All right, and the reason this is kind of exciting to us is because, we don't want to store these passwords in plain text, but maybe we could store the hash of the password. Right, so here's our previous passwords, right? And again, remember, a couple of them are very common. And we're going to hash them, right? The hashes are long enough that it moved some of our users off the slide. Don't worry about that. All right, so these are I just took the hashes of those passwords. Let's forget our adversary for a moment. Let's just make sure that we can still use this to authenticate users, right? Because if we can't uphold our policy, it doesn't matter like how secure we are against various threats. We're not doing what we tried to do in the first place, right? So to authenticate users doing this, we're basically going to add one more step. All right, I own this server. I stored hashes of passwords. You show up, you input your password, all right? I take the hash of it, I compare it to what's in this table. Right? It is unlikely. It's incredibly unlikely that someone is going to show up and, pretend to be you and put in a different password and get the same hash. Right? That's what we get from these functions being one way. Right? So this is still looking good to us. Right? At the very least, we can authenticate our users. Right? And the adversary can't just read passwords directly from the table. Right? So if Howie comes in and he sees this table, he can look at many of these, these hashes, right? He can look at user 6's hash, but knowing that string, right? These functions are one way. There's not like an inverse hash function. He can't go backwards, right? At least not right now. Right? So this seems like progress. At least we've eliminated the first problem, which is that Howie could just read the passwords from the table, right? But I told you this wasn't going to work at first. Here's the reason it's not going to work right now. Right? It is very easy to compute hash functions. Very easy and very fast. Right? So, and we're going to assume that whatever hash function we've chosen, Howie knows what it is. So Howie's going to put in a little bit of work ahead of time. And, before he has access to this table, he goes ahead and takes just a bunch of passwords. Like so many passwords, figures out their hash ahead of time. All right, which means, let's see, you can see in this table, I have both some common passwords and some less common passwords. Right, so I'm going to do another poll. This is a poll of guessing. Okay. I have to share the results from the previous poll. Okay, I want to do the second poll. Zoom is impossible. Okay, we won't do a poll. I'll ask you in the chat. Let's say that Howie wants to make a table like this, and he wants to do it for the top 10 million passwords, the 10 million most common passwords. How much time do you think it will take Howie to figure out the hash for all of those passwords? So to take all 10 million of them and calculate 10 million hashes. Just give me a guess. There's nothing that I've told you that means you'll actually know this. I just wanna know. What do you all think about hash functions? A few seconds, 5 seconds, 1,000 million nanoseconds. Okay. Okay, you all are all definitely, that's sure, Julian. You all are in the right ballpark. So I did this. It took 8 seconds on my laptop. My laptop is fine. It's not like, it's not a supercomputer. It's just a normal laptop, right? So how we can make this table so quickly that it's actually not unreasonable to imagine that he would have most passwords. It's very, very easy to make this sort of data structure, mapping passwords to hashes. And you can see now how he would use this, right? You can say, okay, here's this hash. This is the hash of the password 111.111. And here we see it show up in various places in our stored data. So we know those users' passwords 111.111, right? And again, he can do this with even less common passwords because it's so easy to build this table. I am often going to refer to this table, just so we have something to call it. I'm going to refer it to a rainbow table. The fact that it's a rainbow on the slide is a coincidence. That wasn't intentional. A rainbow table is a real data structure used for this purpose. In practice, they are much more complicated than what I'm showing you in the slide, but it's easier to talk about if we have something to call this. All right. So this is not great for us. We had a great idea. It hasn't panned out. All right. And the reason it hasn't panned out, it's because hash functions in many places, we want them to be fast, right? You all may have seen hash functions in the context of like data structures, like creating hash tables or something like that. In those contexts, you want to calculate a hash in like a nanosecond. You want it to be so fast. In the context of cryptography, though, we would like that to not happen, right? So we're going to make a slight tweak to our hash functions. Oh, Miller, great question in the chat. If there's a single character difference between two passwords, how much different will their hashes be? We would hope extremely different, because if not, we would be opened up to all sorts of other attacks, right? So in many ways, the hashes look random, right? So we're gonna change these hash functions a little bit, and we're gonna make them slower, all right? So I'm gonna start talking about what we call in this class slow hash functions, right? The rest of the world would probably talk about these as key derivation functions, okay? But I do not want you to have to remember two totally distinct terms. And it is important to me that you remember these are still hash functions with all of the properties they had before. The thing that has changed is this computation is going to be slower, right? Instead of, say, taking a nanosecond to calculate a hash, it's going to take a second. Right, so still very easy to do on the authentication side, and we'll see what we think Howie can do here. All right, so again, we're going to call them slow hash functions. Right, if you're sitting in lecture and you're like, well, why did Katrina even bring up the first hash function? Right, the first type is what you're most familiar with if you're coming from other areas of computer science. But now in cryptography, we actually want these to be a little slower. All right, so same table. I've taken a slightly different hash. That's why these random strings look different. Don't worry about the fact that they're a little bit shorter than before. That's not going to cause us any problems. In terms of authenticating users, we authenticate them in the exact same way. Right? You input a password, I take the hash of it, I check whether that hash is equal to the stored hash. All right. So authentication-wise, things are looking okay. Our question now is, well, how are things going against our threat? Can our adversaries still make this table? Right? In theory, yes, but it's going to be so much slower that realistically, now it's really only feasible for an adversary to be calculating this table for the most common passwords. All right, so we're gonna expect Howie to have a table that looks more like this, right? And you can see that, again, he's got the hashes for these 3 common passwords. We see those hashes show up in the table, right? We can infer the passwords for those users from that information. But, this table, say of like the top 10 million passwords, it took on the order of days to create, right? Not seconds, right? So in some ways, what we've done is for our adversary, we've pushed the time scale of this attack out farther, right? What exactly makes it slow? The way that the hash function is calculated, like it will just take a longer time to do these calculations. I'll let anyone who wants to describe hash functions in more detail from the staff feel free. But like the way it is computed will take longer. All right, it's not just like we're gonna make you wait for the result. It just actually takes more time to do the computation. Okay, so we are still not satisfied with this. All right, we would like we'd like Howie to not be able to do this at all. Right, here's what we're gonna try to do. Right, we're gonna try to make it more difficult for an adversary to pre-compute hashes, even for common passwords. Right, notice that all of these tables, all of these rainbow tables that our adversary has been building, they can build them ahead of time. Right, we'd like to prevent that. Right, and one idea to do this is to add some sort of randomness into this system. Right, and this is something you should be able to think about, even if you feel like you hate math. All right, if we want to make something harder to do up front, add some random element to it, right? Because then it's very unlikely that we could pre-compute something. So here's what we're going to do. It's going to look surprising at first. Just bear with me in any surprise. We're going to associate a random value, which in this context we call a salt, with each user. All right, so you can see I have random strings here. They are stored in plain text. They are not a secret. Right, when Howie comes back, when our adversary comes back, they will be able to read the salt directly. Right, so you can be surprised by that for now. All right, that's fine. Here's how we're going to use it. We're going to take this salt for each user. We're going to concatenate the password and the salt and hash that. All right, that is what this notation here at the top means. That vertical bar, so password bar salt, that's just password concatenated with salt. Like in Python, like we're adding 2 strings together, right? So we're concatenating them together. In the world of cryptography, we like to use a line, right? So this is what we're going to store now. First, let us just make sure that we can still authenticate users, right? No one's attacking us yet. We just want to see how we would use this. All right, well, we can still authenticate users. It's still okay. Again, you show up to my system, you input your password, right? I'm going to go into this table. I'm going to look up whatever your random salt is. Remember, it's just stored in plain text, right? It's right there. You're going to take that salt, take the password that you inputted, concatenate them together, hash that, and check that it matches what I have stored in the table, right? So again, we've added like one more step to authentication here. Right, but it's okay. We can still authenticate users with this. We're just basically you input a password and I need to do the same calculations again and check that the hashes match. Right? But what we really care about is Howie. Is it feasible for an adversary to make the same table as before? Right? Think about what an adversary has to do now. They would have to like create this data structure for every possible salt, right? I want to say like 16 character salts here, right? They're relatively long. It is impractical to imagine that our adversary would compute, a table, even for the most common passwords, right? For every possible salt ahead of time, right? Now, if say Howie shows up and they want to target, Howie wants to target a specific user, right? Howie can see user 1 salt right here, right? It's random. He could start creating a rainbow table for that salt. And maybe he gets lucky. Maybe 10 days from now, it turns out, yeah, this user had a really common password, right? How he figures out what it is. But again, we're pushing the time scale of that attack off by days, right? It's possible that, in that amount of time, the system may have detected, right? Detected some sort of compromise and sort of said to users, hey, you have to reset every password or something like that, right? We've made it much less enticing for adversaries to attack these systems, right? I will tell you that a lot of times if you see, if you hear about like a big username and password, breach, like some system gets attacked and usernames and passwords are exposed. A lot of the time, it's systems that aren't storing passwords in the correct way, right? They're not properly salting their hashes. Maybe they just forgot the salt entirely, which is not great, or it's not random in the same way that it needs to be, right? So everything we're doing here is just making it harder and harder and harder and harder for an adversary to target users. And you can imagine if you have a strong password, this process is it's gonna take so long for Howie to break into your account to steal your password. All right, so this is how we're going to go about storing passwords in most systems, right? And we still have a few things to talk about, but I do want to bring up a couple of themes that you've seen so far, right? Even in this just like 20 minutes, right? Everything that we've talked about here, this is something that you as a system designer can do, right? To help secure your users, even though they're not perfect, right? We had to deal with the fact that users, they don't pick great passwords. They just don't, right? We still want to try to uphold a goal even in the face of that, right? You've also seen, okay, storing sensitive data in plain text is bad, right? Storing hashes is better. Adding randomness helps, right? Hashing, randomness, these are big themes in cryptography. And so we see them applied to systems in this way a lot. Right, so this should give you a sense of how to store passwords securely on a server, right? And this is a robust password storage solution. It is fairly infeasible for adversaries to make the styles of attacks that they want to do here. Right, but since we're talking about passwords and passwords are so common, I want to touch on a few practical issues, right? Because these are all things that we would have to deal with in the real world. So we're going to look at some just slightly tweaked threat models. Mostly, I just want you to be aware of these things and sort of how they interact with the system. We're not going to go nearly as in depth into kind of the like hashing and randomness and all that stuff, right? So one of the things that we would want to try to do in our systems, if we're going to use usernames and passwords, we would like to limit how frequently users are transmitting passwords, right? For a number of reasons. If I have to type and store and transmit and like check my password over and over and over and over, I'm probably going to be more motivated to pick an easy password, right? A short password, one that I don't mind typing. We could try to automate that process, but it means, okay, then we have to store our process somewhere. And you've seen where storing passwords, it's not easy, right? So a common thing that you will see to help limit transmission of passwords is cookies. Right? I feel very confident saying that you have encountered cookies on a website at this point in your lives, right? These allow users to authenticate themselves for some period of time, right, without repeatedly transmitting passwords, right? So before we go into like what is actually in a cookie, potentially, this is roughly what happens. So we've got a client, we've got a server. You all know this model. This is like everything. There's a client, there's a server, right? The client is going to send over their username and password. We're going to deal with that whole problem next week. All right. The way I've drawn it here, it looks as if I'm just sending my username and password totally in the clear over a network. This would be a horrible idea, but that is a horrible idea for next Monday. Right. We're going to send our username and password, and then server's going to send us back a cookie, right? Assuming that I've given the correct username and password combination. Right. And that's what I would use to authenticate myself on future commands. Right? So these cookies are kind of like temporary passwords. They're good usually only for a limited time, right? Could be minutes, could be a small number of hours, but like a pretty limited amount of time. Right? So let's, what are these like? Right? And for me to talk to you about what's in a cookie, I need to give you one more piece of information, which is that typically to make this work, The server itself is going to have some sort of secret piece of information. We're going to call this the server key. It's stored on the server. We're gonna assume it's stored very securely, right? We're not worried about the storage of that for this example. So the server has this unique key tied to it, right? Here's what a cookie might look like, right? This is sort of a basic idea. They can get more complicated. This is a basic idea. And you can see here it has, okay, the user's username. So this cookie is tied to this user, right? Howie can't show up and try to use it for himself. All right, it has an expiration. So there's a time limit on this. That would be the time limit. And then there's this hash, right? And it's a hash of the server's key, so the secret key, along with the username, along with the expiration, right? And the threat model we're thinking here, it took me some words to describe, right? We're imagining an adversary that is maybe observing this cookie and maybe wants to try to get the user's password. That'd be really bad. Or wants to be able to take this cookie that it observes and manipulate it in some way that they could continue to log in as that user, right? And if we spend a little bit of time thinking about that, you can see that, okay, maybe Howie grabs this cookie from us, right? If he wanted to change the expiration date, or if he wanted to change the username, right? He would also need to somehow change this value, this hash value. That is not something that Howie can do without knowing the server key, right? So these two pieces of information, the username, the expiration, they're part of the input into this hash, as is the server's secret, right? Which means that the server is the only one that can compute that hash, right? So even if Howie is able to see this cookie, maybe he kind of grabs it and masquerades as a user for a short amount of time. He's not going to be able to edit the cookie in a meaningful way, right? But again, we're not going to go super in depth into this. Just want you to have an idea that this is out there. This is another thing that we think about, right? One other thing that we think about in the world of passwords is, suppose we have a slightly different threat model. Suppose we have something like a phishing attack, right? What is going on in a phishing attack, and the way that we're going to think about it here is, imagine, okay, I'm running my Katrina's Amazing Web Suite. You all are logging into my server so you can buy your llamas and whatever. Howie's going to try to set up his own server, right? Howie's evil web suite, okay? And he's going to try to convince you that that's Katrina's Amazing Web Suite, and you should go over there and log in, right? So here's a protocol. I think that these are very neat. Here's a protocol that we could use to try to get ourselves out of that style of attack, right? These are known as challenge response protocols. They let us authenticate users without ever transmitting the password. And part of the reason that I want to show them to you, one, I mean, they're interesting and they come up all the time in this type of work, but also it's kind of wild, right? This is a wild statement. We're going to authenticate a user without them ever transmitting the password, right? So here's how it's going to work. We're not going to worry about an attack just yet. And for the moment, for purposes of illustration, we are going to imagine that our server is storing just usernames and passwords. That's bad. I already told you that that's bad, but I need that to illustrate how this works for right now. All right, so we have our client, we have our totally valid server. All right, so instead of this client sending over its username and password, our server is going to send a random number. This is the challenge, right? The challenge is this random number. And our client is going to send this back, right? It is this hash of their password concatenated with that number, with the challenge, right? And so it looks like this. It looks like this weird hash, right? The server on their end can compute that same hash, right? They're storing the password and check it, right? So that's kind of an interesting like reversal of this process, right? Now let's imagine our adversary, right? They own a server trying to convince the user to just send their password to this server, right? So this is our adversary owned server. They don't know the password. They're trying to learn it, right? Well, if our client is expecting a challenge response protocol, right? If they show up and they say, I know Katrina's Amazing Web Service Suite. I never know what I call it at the first day of class. I know that the Katrina's amazing web, whatever, uses a challenge response protocol. So I'm expecting a challenge response protocol from the server. So Howie says, okay, I will send a challenge. All the adversary learns is the output of this hash, right? They're not going to be able to reverse engineer this, at least once we get into a world where we're using our properly salted hashes and all of those sorts of things, right? So again, we're not going to go super into detail of either of these things. The reason I'm bringing them up is because you should understand that when we're thinking about passwords, right, we have to think more just about how we store them. We also have to think about them being transmitted, right? Partly because that is open up to other attacks, but partly because if our users are going to have to type their password over and over and over and over, it's even more likely that they're going to pick bad ones. All right. So now, with all of that said, why use passwords at all? Right? What are the alternatives? Okay. There are a couple of alternatives, and they all have their own trade-offs. Right? So a couple of things I saw Johnny mentioned early in the chat, a password manager, right? So password manager, piece of software, can do a few things, can automatically generate good passwords for you, can sort of keep track of your passwords. It's a little bit less convenient, but it can keep you from picking, bad passwords, reusing passwords. At the same time, you've now put trust in a company, right? Do you trust the people who wrote the password manager? That's a question for you to think about. All right, other not quite alternatives, but sort of additions to passwords, or to use something like two-factor authentication, right? You will probably do that occasionally to log into things at MIT, right? Where you go to log in and MIT sends a text to your phone and you can't log in without that sort of little secret that they text to your phone, right? It adds an additional step, right? I end up doing this all the time, and some days it really annoys me, right? But if an adversary wanted to compromise my account, they would need my phone, which is unlikely. There are lots of other ideas. We can do things like biometric passwords, right? Fingerprint scans, retina scans. Some of you all even like facial recognition, right? If you have certain phones, right, you might do this all the time. Those are very interesting. It does make it hard to be anonymous, right? Your accounts are tied to you as a person. And it's hard to imagine, what do you do if your password in that sense is compromised, right? Is there a way to reset it at all? Oh, Savannah in the chat. I think that is a very great point. Something that happened to me a couple years ago, I had one of the advisors in the department was abroad during registration week and couldn't log in to access any of their advising information because their phone didn't work abroad. And so they couldn't do the two-factor authentication, right? So there are these alternatives, but they have their own trade-offs, right? There are trade-offs of just convenience. There are trade-offs of trust, right? Are you sort of adding people to your network of trust? There are trade-offs in, again, what if my fingerprint is compromised? I can't get a new fingerprint, right? How do you deal with this, right? So sort of better solutions in some way typically mean more complexity and less convenience, right? So we still use passwords a lot, right? We've taught you now how we store them securely on machines. And again, it's not that it would be completely and totally impossible for Howie to ever figure out your password. But by storing these salted hashes, we've made it much less enticing for him to do that. That attack takes much more time to figure out, right? So again, there are trade-offs here. If you want to take away some general lessons from this, which I hope that you do, that is the point of learning. One of the lessons that I think we get from passwords is knowing that our users aren't perfect, right? We cannot rely on users to pick strong passwords, right? We still want to support those users. Okay, so this is where we're going to end for today. What we're going to talk about on tomorrow recitation, you're going to finish up RAC. So tomorrow's recitation is really unrelated to anything we did in lectures today. What we're going to start talking about on Wednesday and into Thursday is sort of some different ways that an adversary with access to a machine could try to read data. Because if you're thinking of this threat model and thinking like, I don't quite see how Howie would be able to get that table unless he was a system administrator. I will show you on Wednesday, and you will learn further on Thursday, some ways that Howie would be able to get that table. All right, so that is where we're headed the rest of this week. Next week, we'll start worrying about adversaries on the network. But that is it for today. I will hang out if there are questions. Let me stop sharing everything first.